Welcome in to another new podcast from the Association for Materials Protection and Performance. My name is Ben Dubose, and I'm a staff writer with Materials Performance Magazine, also known as MP. Today, in the latest episode of our MP interview series, we're launching a new mini-series, if you will, to spotlight some of the newer technologies that are designed to help out with the ongoing war against corrosion. In late April, as some of you may be aware, we announced the 2021 winners of the MP Corrosion Innovation of the Year Awards program. These winners, which you can read about at materialsperformance.com, were graded and judged by a panel of industry experts across numerous fields and sectors within corrosion control. Anyway, over the coming weeks and months, we're going to be inviting each of these winning groups onto the podcast to talk a bit more about their new innovation and how they think it can potentially change the corrosion industry in the years ahead. To start off the series, I'd like to welcome in Harvey Hack and Jim Wingasson of Northrop Grumman Undersea Systems. And I think a good place to start, I'll let you begin, Harvey, by introducing yourself, and then Jim, you can do the same. Tell our listeners a little bit about your career in the industry and your role with the company now.
Sure. Hello, my name is Harvey Hack, and I'm one of the inventors of the NiobiCon technology. I'm a PhD metallurgist who spent the first 25 years of my career working for the Marine Corrosion Branch of the Naval Surface Warfare Center, performing marine corrosion research and failure analysis. I have now spent about 25 years at Northrop Grumman Marine and Oceanic Systems, trying to control corrosion on undersea hardware. I'm a past president of NACE International and chairman of the board of ASCM International. Also on the NiobiCon team are Keith Johans and Megan Owens.
Hi, my name is Jim Wingasson. I'm the other inventor of the NiobiCon technology. I'm an electrical and mechanical engineer, and I've been with Northrop Grumman now for about 20 years. My work at Northrop Grumman as an electrical engineer has encompassed analog design, power, RF, and embedded design. Most of my mechanical engineering work has been in electronics packaging, everything from microelectronics to making investment castings for inertial measurement systems. Outside of work, I'm very passionate about STEM education and more recently, financial literacy for children, and I volunteer a lot of my time towards these subjects.
So now that we have your background, I want to transition to more current times and talking about the NiobiCon, the winning innovation. How does it work? Just give us, if you will, a bit of, I suppose, an executive summary about your winning innovation.
Sure, this is Harvey. NiobiCon is an underwater, wet-mateable electrical connector where the electrical contacts don't have to be protected from water since they're made from a metal that grows its own insulating film, removing the need for O-ring seals and dielectric materials. All other underwater connectors seek to exclude water from electrical contacts made from traditional materials, such as brass, in one way or another. In our design, the contacts are flooded with seawater, and the contacts are made from transition metals, such as niobium or titanium, that grow their own insulating film when exposed to water. Upon mating, this film, which is on the order of 100 nanometers thick, is locally displaced, allowing for metal-to-metal contact. When demated, the small areas where the film was displaced regrow their insulating film within milliseconds. These connectors have no moving parts, no components affected by pressure, and are resistant to corrosion, greatly improving reliability of electrical connectors underwater or in other corrosive environments.
So you touched on this briefly, but what was the driving force for you guys to develop this technology? What was it in terms of an industry need that sparked this particular innovation?
This is Jim Wingasson. So at Northrop Grumman Marine and Oceanic Systems, we use a lot of underwater electrical connectors, and we recognize the need due to the current connector technology, lack of reliability, expense, lead time, and other operational issues. We invented this new connector technology while investigating a way to efficiently recharge a vehicle underwater. Traditional connectors were too hard to adapt to the geometry of a docking station, and inductive chargers had too high of a power loss and they're too physically large to fit in small vehicles. Using a contact material that doesn't corrode or short out in seawater, even with an applied voltage, was the logical solution to that problem.
What are some of, specifically, the historical limitations with these types of connector technologies?
Hi, this is Harvey. The seals in the traditional connectors are a frequent point of failure. Pinched O-rings, nicked rubber seals do happen. Connectors that use dielectric bladders have limited mating cycles and high mating forces, as well as being expensive. Some connectors have depth limitations or limits on storage temperature due to the use of elastomers or dielectric gels. This makes current connectors for underwater less reliable and more expensive than is desired.
So how long have you all been working on this from a timeline perspective?
This is Jim Wingaston. The first patent was issued in 2015. However, our work on this started several years before then. It took us a few years for the idea to take hold and get funding to develop our concept further. Our initial funding came from a Northrop Grumman innovation program called SPARK, and later our funding has come from both customer sources and Northrop Grumman Corporation business development coffers. Initially, the work was done primarily by Harvey and I, but with the addition of Keith Johans, our licensing manager, and Megan Owens, who's our newest addition to the team, our work has definitely accelerated.
We talked a couple of minutes ago about some of the historical limitations of connector technologies. How does NiobiCon overcome those types of challenges?
Oh, this is Harvey again. Since NiobiCon allows the contacts to be wet, no seals are necessary, meaning leakage into the connector is no longer a reliability issue. This technology is essentially unaffected by temperature or pressure, working in freezing or boiling water, with or without salt or dissolved oxygen, and in strong acids. Because there are no moving parts, connection force is minimal, wear is not an issue, and close tolerance fits aren't required, lowering production costs and increasing reliability.
So what type of field testing has there been to this point? What have you guys found when you're doing your testing procedures?
This is Jim. We just delivered a set of underwater communication cables with connectors to a government customer for use on an underwater vehicle. These cables had to pass rigorous testing, including pressure and thermal cycling, as well as mating cycling. And our connectors passed all these tests.
Wow, that sounds really good. Are there any changes or tweaks that you're potentially making as a result of user feedback from this?
This is Harvey. Our initial design is just now beginning production, so we've not yet delivered commercial connectors, but we're already working on optimizing high power contacts so that they'll perform as well in air as they do in underwater. But we're also starting a design that is optimized for gigabit level Ethernet for high data rate transmission.
So we've been talking about the field testing and, of course, the process to developing this NiobiCon technology. In terms of scaling it up, what are the next steps for you guys when it comes to commercialization?
This is Jim. We want to get connectors into the hands of the public to get their feedback. A commercial style 8-pin connector is now available for sale by our manufacturing licensee, Icon Systems, located near Chicago, so that potential users can evaluate it themselves to see if it will work in their applications.
So what are the primary challenges when it comes to this process, and how do you plan to address those?
This is Harvey. The primary challenge is one of education of the user, as this technology is fundamentally different than they've encountered. As an electrochemically based connector that operates strictly with direct current, some things are different than for traditional connectors. The water surrounding the contacts doesn't affect the operation of the connector, but does affect certain traditional measurements. For example, contact resistance must be measured with a Kelvin technique and not with a typical resistance meter. Pairs of DC contacts immersed in the same seawater environment that have applied different voltages must be isolated electrically from each other, or they'll interact in ways that wouldn't occur in an air environment. Understanding these design challenges will allow users to get the full benefit from this technology.
So what's on the horizon in the near term, the next few months, or I suppose a couple of years? What are the next steps moving forward?
This is Jim. We would like to get an evaluation connector into the hands of potential users so they can see if this technology will work for them as well as we believe it will. We are currently negotiating to get additional licensees for development and production of this technology, and we are filing patents internationally as well. Finally, we are expecting to have additional U.S. government users very soon as the technology becomes incorporated into military vehicles.
I think it's clear at this point what the primary objective is, but what are some of the other benefits that potentially come from NiobiCon?
Well, this is Harvey. Electrical systems which aren't necessarily always immersed, but may be subject to alternate wet conditions, could have their reliability considerably improved by using this technology. Certain connectors in automotive, aquaculture like fish farming, oil and gas, and agricultural applications will get huge maintenance savings by not having to periodically replace the connectors. The NiobiCon technology provides a previously unachievable level of design freedom for underwater electrical connections. Things that were previously only achievable in the air, such as having exposed electrified rails that a vehicle could land on to charge its batteries, are now possible to do underwater.
For anyone listening that wants to get more information from either of you or learn more about NiobiCon, how can they get that?
Well, we expect this technology to significantly disrupt the traditional connector market for any application that operates in a corrosive environment. Additional information and videos of this in operation can be obtained at our website, which is northropgrumman.com/NiobiCon, NIOBICON, or you can always just Google NiobiCon. Licensing information can be obtained by contacting our licensing manager, Keith Johans, and he can be reached at keith.johans, JOHANNS, @ngc.com. Anybody interested in buying a connector should contact Icon Systems LLC sales engineer Robert Siz at rczYz@iconsystems.com.
Sounds good. And folks, that's where we will leave things for today's episode. If you want more information, of course, Jim just gave you the details for Northrop Grumman, but you can also check out the AMP website at ampp.org for news pertaining to the association, and you can visit materialsperformance.com for all sorts of news and information related to the corrosion control industry. Also, if you have not already subscribed to this podcast, or if you haven't left it a 5-star review, please do. We're available at Apple, Google, Spotify, and virtually every major podcast distributor. With that, we'll sign off. For Harvey Hack and Jim Wingasson, I'm Ben Dubose. Thanks as always for listening, and please come back soon for another podcast episode from the MP Interview Series.